So the chain rule is one of, I think, the most confusing rules to get first, but once you get it, it's one of the easiest rules to apply. So far, we have rules for sums, differences, products, and quotients, right? So what is another kind of function you can have? Like this is an example of one. The square root of x squared plus 1. That's not a product, it's not, there's a sum in there, but what officially is it called? That's called a composite function. Which means that you have one function inside of another. So take this function y equals root x squared plus 1. Back in the chapter 1 where you were reviewing some prerequisite stuff, you were asked to write this as f of g, like to find the two functions that were composed. Or f of g of x. So in this particular example, what is g of x? What is f of x? Is the g, and f of x is the root x, right? So what I'm going to do in class is I'm going to refer to this x squared plus 1 as the inside function. This root x is the outside function. And that's because x squared plus 1 is inside of a square root. Does that make sense? Okay. Alrighty. Now, here is what the derivative form says. If you have a function capital F, and F is defined as F composed G, then F is differentiable. If F is differentiable, then here is its derivative. It's F prime of G times G prime. So let's talk about what that means. So first of all, what function is F? Is F the outer or is F the inner function? F is the outer. G is inner. So f of x is f of g of x. What this formula says is f prime, capital F prime, is little f prime of g times g prime. So what does f prime mean you do? Take the derivative of the, which one, outer or inner? Derivative of outer. And what's inside of it? Just regular g, not differentiated, right? So this is the original, not differentiated g, and then multiplied by derivative of the inner function. So that's what the rule technically says you're supposed to do. Okay? Does that make sense? All right, we will apply it in some cases, and we're going to do so much, but you're going to have to, you're going to have to get used to it. The reason that it's true comes from that limit definition, so I'll tell you what it is, but you're not going to reproduce this. Remember that when we took the derivative of a function f of x, one other way to write that was the limit as x goes to a, f of x minus f of a over x minus a. That was the first way we did it, right? And this was specifically at the point x equals a, but so it turns out that proving this thing, the easiest way is to use that definition. The derivative of f of g of x is the limit as x goes to a, f of g of a, f of g of x. I wrote the wrong thing and now I can't erase it. Yes, I can. F of g of x minus f of g of a, x minus a. So just with f of g instead of f and just plain old f. Now the clever thing with the proof of the product rules, we had to add and subtract something. The clever thing with this is you have to multiply and divide by something. You write this as f of g of x minus f of g of a over g of x minus g of a times g of x minus g of a over x minus a. Do you at least agree that that's true? Is it okay to do that? Because I'm multiplying by 1, right? Because I did it in the denominator and the other numerator. And this first expression, well, this last expression, that's g prime of a, right? The first expression is f prime of, you see how it's got g's plugged in instead of just plain old x's, right? So that's f prime of g of a. So that's a technical reason why this rule works. What you're just going to have to do is use it a whole lot. So it's helpful to recognize the outer and inner functions, but the point is differentiate the outer, leave the inner alone, multiply by inner's derivative. Okay, let's do an actual example. So I have 1 plus 3x to the 9th. So before knowing this rule, your only option would be to multiply 1 plus 3x by itself 9 times. You don't want to do that, do you? No, I don't either. So the derivative is, so what is the outer function here?
X to the 9.
X to the 9th. So you differentiate that. What's the derivative of something to the 9th?
9 something to the 8th.
9 something to the 8th. And what this rule says, the whole fact that it's f prime of x is f prime of g times g prime, it means that inside your f prime, the g remains unchanged. So in here, we still have 1 plus 3x. Our inner function's unchanged, we just differentiate the thing and stuff around it. And then you multiply by the derivative of the inside function. What is the derivative? What is the inside function, first of all?
3 plus 3x.
What is its derivative?
3.
3. And that's it. So this is going to be y prime equals 27, 1 plus 3x to the 8th. There you go. So you differentiate the outer, leave the inner alone, multiply by inner's derivative. It gets more complicated if the derivative of your inner function is more complicated than this thing. But the basic idea is you differentiate one function at a time. Okay, this one almost the same thing, right? So this is the same thing as x squared plus 2x minus 5 to what power? Negative 9, great. Is that all right? Now you're going to take the derivative.
That's pretty smart.
Yeah, you could use the quotient rule,
That's what I was thinking.
but it actually turns out that often making quotients into products is easier. So, and also it's especially easier if your numerator is a constant. Does that make sense? If your numerator is a number. But even if the numerator was x, you could just write it as x times this thing to the negative 9th. That would also work. Okay, so what is this derivative? First you pull the power down and it's negative 9. Does the stuff inside change? Nope. And then what's negative 9 minus 1? Negative 10, great. Multiplied by the derivative of the stuff inside, which will be 2x plus 2. And then just write your final answer sort of in the original form that it was, as in negative 9 times 2x plus 2, the x squared plus 2x minus 5 goes back in the denominator. Is there anything else we can factor out? The 2. So this could be negative 18 x plus 1 over x squared plus 2x minus 5 to the 10th. Is that all right? Okay. Okay, in example 2, notice that A and B are awfully similar. So in A, you take x, cube it, then apply cosine, right? In B, you find cosine, and then you cube the result that you get. So in this one, who's the outside function? The cosine x. So y prime will be, okay, what's the derivative of just the cosine? Negative sine. And the inside function remains unchanged, multiplied by inside function's derivative, which is 3x squared. Great. So this is negative 3x squared sine of x cubed. Is that good? All right. How about part B? Cosine cubed x. That's the same thing as cosine of x raised to the third power, right? Okay. So what's your outer function here? X to the third, exactly. So if you differentiate that, you've got 3 stuff to the power of 2 times the derivative of the inside stuff. And so what's the inside stuff? Negative sine x. So y prime is negative 3 sine x cosine squared x. It doesn't matter if the sine comes first or the cosine, but it's nice that they have negative 3 there. And just one thing about notation. Why is it bad to write this?
Because it's like
What does it look like? Subtraction. So make sure you do something like that to make it obvious that it's multiplication, okay? But it looks a lot like subtraction. I know you probably don't mean that, but just it looks that way. It happens. I grade a lot of papers, so I see a wide variety of answers. Okay. Now, this rule gets more complicated when you start to mix it up with other rules. I know. So let's start the problem by writing down what rules we're going to have to use. So the chain rule, because you've got stuff to the 5th power, right? What is your inside function? It's a quotient, so what rule has to be applied to do that thing? The quotient rule to do the chain plus, but at least that one has a fun rhyme, so And I'll just do this in a couple steps. So f prime, so you've got stuff to the 5th, right? So that becomes 5 times stuff, unchanged stuff, to the power of 4. Multiplied by the derivative of x plus 5 over 2x minus 1. That d over dx is a way of saying take the derivative. You could also put a prime sign like around the parentheses. That would do notate the same thing. Does that make sense?
Where?
If instead of putting the d over dx here, if I put a prime sign on that, that means I'm still going to take the derivative of it. Does that make sense?
Yeah.
Okay. So either one of those notations is fine.
Does it matter if you mix symbols? Like you start with...
Yeah, I started with f prime, but that's just the thing because you typically use that when you have f as opposed to y, then you can use either. I don't think it's really a big deal. The only problem that I have is occasionally my primes start to look like 1s. Does that make sense? That's probably why. So I don't think it's not a problem to mix notations. I don't think so. Okay, so the 5 stuff to the 4th is all done. So I'm just going to copy it down to the next line. And then the derivative of the next thing, you've got to use the quotient rule. So that's low d high. What's the derivative of that upper function? Yep. Low d high minus high d low, which is 2, great, over 2x minus 1 to the squared. Great, good. Okay, So I've got 5x plus 5 over 2x minus 1 to the fourth. Now in the numerator, 2x minus 1 minus 2x minus 10, I believe. Do you agree? Okay. What happens to the two x's? They cancel. So let's just cross them off lightly. So that's, in the numerator you have negative 11. Can I multiply that by the 5? Is that okay with you? So it'll be negative 55. And I'm going to write that as x plus 5 to the fourth. What is the power on the 2x minus 1 if I account for both denominators? I don't think it's cubed because, oh, I see why you say cubed, but it's not. This 2x minus 1 is also raised to the fourth power. So the power on this is actually 6. I mean, it's tricky, but it's also really good review because you can't forget the quotient rule just because you're in the chain rule, like, you know, for the day, right? It's really good review to reinforce the rules you learned yesterday. Does that make sense? Okay. All right. Ready for the next one? Okay, that was chain quotient. What's this next one gonna be? And it kind of is, I kind of kept, do the chain rule first and then comes the quotient rule, right? And then what rule are you gonna have to use first? Product. And then when you're doing your product, differentiating either one of those things is going to involve the chain rule. I knew a high school AP calculus teacher who would make his students sing like the song Chain of Love or something like that if they ever forgot to use the chain rule. He tried to humiliate them into remembering it. Yeah, pretty hilarious. Okay, so f prime of x is the derivative of 2x minus 1 to the sixth times x cubed minus 2x plus 1 to the third plus 2x minus 1 to the sixth times the derivative of x cubed minus 2x plus 1 cubed. I'm purposefully taking it a little bit slow. If you can do this a little bit faster once you get the hang of it, that's okay. Does that make sense? Do you see what I'm saying there? I'm saying differentiate this thing, leave the next one alone, right? That's just the product rule. Does that make sense? Okay, so this first thing, I'll do it in purple. What is its derivative? First the 6.
Times 2x minus 1.
And then times what? Because of the chain rule.
X to the third minus 2x plus 1.
Times 2. And then x to the third minus 2x plus 1 cubed. The 2 came from the derivative of the 2x minus 1. That is inside the sixth power. Does that make sense? Okay, we good with that? Okay, then plus 2x minus 1 to the sixth times 3x cubed minus 2x plus 1. What's its new power? Squared. And what do you multiply that by because of the chain rule?
3x squared minus 2.
3x squared minus 2. Okay, so write that down. I'll pause, drink some coffee, let you catch up. If you could have done that first step right away without having to write down if you could have done the second step without the first step, that's okay. Does that make sense? Okay. Now this thing does simplify down rather significantly. The way that it simplifies down is by taking out greatest common factors. So, and it's easiest to just look at it term by term. So with first you have the constants. You've got 6 times 2, and you have a constant of 3, right? So that 6 times 2 really is 12, yes? Okay, so what constant can factor out here? 3. All right, and then how about this has a 2x minus 1 to the 5th, and this has a 2x minus 1 to the 6th. So you can take out a 2x minus 1 to the 5th. And then this guy cubed, this guy squared. So what can you take out?
That guy squared.
That guy squared. Okay, and then think about what's left behind. Oh, and I said squared, didn't write squared. There we go. Okay, so this was 12. You took out a 3, leaving you a 4.
Times x cubed minus 2x plus 1 to the first power.
Yep. Do you guys get that all the 2x minus 1s were taken out? And all but one of the cubes were taken out. Okay, in the next term, there's a 2x minus 1. Except for the last thing, right? Yep, and so the last thing, 3x squared minus 2, is still there. Does that make sense? Just take it slow and take out this GCF and think what's left behind. And then if you're good to go, start simplifying, just combine like terms inside the square brackets there. Does that make sense? That's the last thing to do. So 3, 2x minus 1 to the 5th, x cubed minus 2x plus 1 squared. Oh, there we got 4x cubed minus 8x plus 4 plus 6x cubed minus 4x plus 12. I think you can see it. Okay, no, it's all good. Everyone has their moments. I have lots of them. 3, 2x minus 1 to the 5th, x cubed minus 2x plus 1 squared. Okay, like term city. 10x cubed plus 12x squared minus 12x plus 6. Do you guys agree with that?
You can factor a 2 out of that, right?
Yeah, but I'm so done with this problem. If you want to factor a 2 out, great. I'm not going to dock you if you don't because it's so disgusting already. Do you see what I'm saying? Like, it's good enough. That's the bigger question there is how do you deal with those things raised to powers? Did I make a mistake?
What is 12x squared?
It's not 12x squared, it's 3x squared. Yeah, I was just testing you guys. Ah, shoot.
I think it's negative 3x.
It is minus 3x squared. Yes, yeah, I was just testing you and you passed. Minus 3x squared plus 2. So we get 10x cubed minus 3x squared minus 12x plus 6. And look, now there's no greatest common factor, so ha, I'm done. Yeah? Ooh, I'm going to change my eraser to being smaller because, you know, it was huge. What does it default to huge? Okay, that's our answer. Okay. Alrighty. So on to some complicated ones. E to the x secant x. So this is an example of first chain plus what rule comes when you differentiate the thing inside. You got x secant, which is x times secant. That's a product. So chain plus product. Okay. So what's the derivative of e to the something? e to that something. So you've got e to the unchanged something, and that was secant, not sine. E to the secant x multiplied by the derivative of that something. I haven't done it yet, but that derivative is of the something. And then the product rule is required to differentiate the something. So if all you had was the derivative of x secant x, which I could have given you yesterday, like that's something you should have been able to do, what would you differentiate first? The x, which would be 1, and the secant x gets left alone, right? Plus x, and what's the derivative of secant? Great. And then is there a greatest common factor that you could factor out? So you got secant of x, e to the x, secant x times 1 plus x tan x. Is it also clear that those parentheses are necessary? Because the derivative of your inside function ended up with 2 terms, not just 1 term. Okay, so there's your derivative, y prime equals that stuff. Nope, the 1 secant x, this whole thing, that's the product rule. Does that make sense? Okay, great. The chain rule is the fact that we multiply that derivative in the first place. Does that make sense? Okay. Does part B look a little scary? Oh my God, sine of sine of sine. You saw the sine. Sorry, I just can't resist such a bad joke. Okay, who is the outermost function? Yeah, right? Sine. I mean, who would have thought? But it's this sine, right? Does that make sense?
That movie,
I-
Signs.
I haven't seen that movie. So what's the derivative of sine? Cosine. And the stuff inside, which is sine of sine, is still there. Multiply by the derivative of what?
Sine of sine.
Sine of sine. So you did one function, derivative times derivative of inside. So that's cosine of sine of sine. They saw the sine too. Sorry. Times. Now, if you're just looking at this part, it's also a chain rule. What's the derivative of the, well, who's the outer function? Sine. What is sine derivative? Cosine. This time it's cosine of a singular sine multiplied by the derivative of that singular sine. And what is that derivative of that singular sine? Cosine. So that's cosine of sine of x, cosine of sine x, times cosine x. Now you're seeing the sine and the cosine. So I think that's what I would call a double chain rule. Do you see what I mean? You do the chain rule twice, once for the sine of sine and then once for one. I don't even think I can say it right. Yeah, twice. Chain rule times 2. Just leave it. There's nothing you can do to it. I mean, you can't say anything is squared because the arguments here, the things inside the cosines are different. So you cannot simplify that at all. That's all. It's it. Yep. You could only say cosine squared of something if the stuff inside those cosines are equal. And the stuff inside these cosines are completely unequal. So you're done. That's it. Crazy, huh? Yeah. Okay. So how do you find equations of tangent lines? You use the blank to find the blank, to find the slope. Use the derivative to find the slope. So use y prime to find m. Okay, great. So first thing is you must get the derivative. So y is equal to square root of 5 plus x squared, which is the same thing as 5 plus x squared to what power? 1/2. Great. All right. So y prime will be, so you've got, who's your outside function? X to the 1/2, yep. So first the 1/2 pulls down. Stuff inside remains unchanged. What's its new power? -1/2. Multiplied by the derivative of the inside function. And that inside function is 5 plus x squared, so what's its derivative? 2x. So simplifying slightly, that's going to be x over the square root 5 plus x squared. The 1/2 and the 2 cancel, right? Woo. Aren't you so happy to use like a limit definition to find that derivative? It's so much better this way. Okay, so now find the slope. What number gets plugged in? 2. 2 over root 5 plus 4. So m equals, I think 2/3. Do you agree? Okay, good. Then plug into point slope. I know some of you don't like to use this, but just like give it a try. Like it actually is easier than like doing the whole find the b thing using y equals mx plus b. So y minus 3 equals 2/3 x minus 2. Or if you get slope intercept form, in case I get mean and ask for it, plus 3 plus 3. So 3 is how many thirds? 12? So 12 minus 4 I think is 8. Do you agree with 2/3 plus 8? 3 is 9/3. Crap! I was just testing you again. Second time today you passed. 2x plus 2/3 x plus 5/3. Moral of story, don't add fractions in your head. Even Juno can't do it. Okay. All right. What was her name in, what was my name in Inception? I don't know either. Yeah, I don't know. The point, I look like Ellen Page is the point. I know it's really bad. Okay. So also you could have this stuff being given like a table of values. So if your function h of x is f of g of x, find h prime of 1. And if you don't have adequate information in the table, like you just say there's not enough information to answer this question. That's going to be like, it'll be multiple choice and website, there's going to be that option. But the point is since h is a composite, to take h's derivative, you need the chain rule, right? So h prime would equal f prime of g, left alone, times g prime. And then how do you find h prime of 1? Just put in 1 and then find values from the table. Yep. F prime of g of 1, g prime of 1. So the things that I'm going to underline in purple are the things that you've got to work out first. You've got to work out that, and you've got to work out that. So from the table, what is g of 1? 2. What is g prime of 1? 6. And then now can you work out what f prime of, do you see this is the x, g of x is 2 there, g prime is 6. So the table's telling you. Okay, and then what is, how would you find f prime of 2? What row and what column? Think third row, second column. rows go across. Columns, like in the Coliseum, columns go up and down. I think it's gonna be 1, isn't it? No, it's not. I was wrong, you were right. Oh, it's this one. That's the third test today. Okay, so what's f prime of 2? 5. So 5 times 6 makes 30. Try part B. It's almost the exact same thing. Just switch the order of the G and the F. Give it a shot, okay? Try. You too, yeah, you. Did you finish it?
What's that?
Part B?
I didn't know there was a B.
It's on your, like right in front of you. That one. Do it. Go,
I
now.
was waiting for you to change screens, I just sit there.
I know, you were just sitting there. Give it a shot. To the lovely noise of construction. We love construction.
It's the job I'll end up in if I fail this class.
It is the job you will have if you fail this class. Yes. Yeah, I don't. It is the job you will not have because you're going to pass this class. And I know some people who like were engineers that went to work construction because they thought it was fun.
It's the job we're going to make easier by passing this class.
Exactly.
There's kind of a difficulty to money ratio that you need to hit in order to be happy.
Okay. Does everyone get the formula that it's g prime of f times f prime? Is that okay? And then it's g prime of f of 1 times f prime of 1. So what must you figure out first? And what is f of 1? 3. And then what's f prime of 1? 4. And then you got to find g prime of 3, which is the last row, last column, right? So that is 9 times 4, which is 36. Great. Awesome. Okay.
It's easier with the table.
Oh yeah, I mean, yeah, it is. Okay. So far you know derivatives of powers, the exponential function e to the x, and trig functions, right? This is the only additional formula you're gonna get today, I'm pretty sure. Yep. It's the derivative of b to the x. In this case, b is any number. Okay, I'm going to show you a couple, like we're going to apply this to a couple functions, and then I'll show you why it's true, okay? So if you had y equals 2 to the x, according to this formula, what would y prime be? So it says the derivative of b to the x is ln b times b to the x, right? In this example that I just wrote down, what is b? 2. So that will be ln of 2 times 2 to the x, okay? What if I gave you 10 to the x? What would y prime be there? Ln of 10. And the question is does this formula still work with e? Let's pretend that we don't know that e to the x is its own derivative. Just for a second, we just know this formula, okay? Applying this formula, y prime is ln of e, right? Times e to the x, and oh, what is ln of e? Yeah, ln of e is 1, so this just equals e to the x. So e to the x is kind of special because in that case the ln and the e cancel, just giving you 1. Is that all right? Okay, so add that formula to your stack of flashcards. By now you should have about 7 or 8 formulas on there, depending if you need the polynomial one. Okay, so here is how you prove it, okay? So you have y equals b to the x. You use clever exponential log stuff. you write this as e to the ln of b to the x. So I'm not going to ask you to come up with that on your own, but do you believe that that's true? Why is this the same thing as that? What is e to the ln of b? Just b, right? Which means then it's b to the x power, okay? It's a clever way to rewrite b using e's, okay? And now what happens to these exponents? They multiply. So y is equal to e to the ln of b times x. And let's just do a quick related question. If I gave you y equaled e to the 4x, okay, for example, what's y prime going to be from the chain rule? E to the stuff times what's the derivative of the stuff? It's just times 4. The derivative of e to the x is just e to the x, right? So e to the stuff's derivative is e to the stuff times stuff's derivative, and stuff's derivative is 4. So how is that going to relate to this? What's the derivative of e to the stuff? You start with e to the stuff times the derivative of stuff, and is ln of b is just some number, right? The derivative of 4x is 4. What's the derivative of ln of b times x? Almost. ln b. Because ln is part of the number. So that just gives you back ln b times b to the x. So that's where that comes from, the chain rule. You're just going to have to use it. Okay, so what's the derivative of this guy? Mm-hmm. Okay, how about this one? This one's a little different because instead of x, what's in the exponent? Cosine. So f prime will be ln of what number? 10 times 10 to the stuff times the derivative of the stuff. So what is the derivative of the cosine of x? Negative sign. Just best to write it in front to make sure the negative's out there. So negative ln 10 sine x, 10 to the cosine of x. So that was applying the formula we just learned. And what is the name of the formula that determined that this negative sign was multiplied as well? What rule was that? Chain. When you have a cosine inside a 10 to the x. It's like if you're writing this as f of g, the g function is the cosine, the f function is 10 to the x. You got cosine inside of sine versus if it was f times g, that would be cosine x times 10 to the x. You see how that's different? The cosine's inside the exponent as opposed to multiplied by the stuff. Okay. All right, next one's an exponent on steroids. You ready? Okay, how many exponents are there? I think there are 2. Do you see that? 5 is raised to the 3 and 3 is raised to the x squared. Do you agree with that? Okay.
So are you allowed to say that the 5 to the 3rd is 125?
No, you're not. Because that would be true if it was 5 to the 3x squared, like they were multiplied. And then you could break it into 5 to the 3rd x squared. That would be okay. But since the x squared is actually another power, you can't. Good question, though. Okay, so first you have 5 to the something. Yeah, 5 to the whatever. So f prime will be ln of 5 times 5 to the whatever times the derivative of the whatever. Okay, is that part okay? Okay, so ln 5, 5 to the whatever. And then just pretend like this is the only problem that you have. What's the derivative of 3 to the something? What was the derivative of 5 to something? ln of 3, 3 to the x squared, and what thing still needs to be differentiated? And x squared, that's going to be 2x. So there's your derivative. 2x ln 5 times ln 3, 5 to the 3 to the x squared, 3 to the x squared. It was that rule we just learned applied 2 times. That's a double chain. The first chain is 5 to the stuff, the second chain is the 3 to the stuff. But I think it might just help if you say, okay, I applied my formula, and I've got a derivative, whatever was inside of that function. And then you just think, okay, this is the only problem I have to deal with now, is how would I do this derivative if that was all that I had?
So you don't have to worry about the 5 to the
I just can't hear because of the construction. What?
Oh, you don't have to worry about the 5 to the third to the x squared.
You can't do anything to it. There's no way to simplify it. All right. So example 10. So back to finding points where the tangent is horizontal. So if you're ahead and you're waiting, how about you find the derivative of the thing in example? Yes?
Oh, you don't think you can.
Oh, there's a b. Oh, I'm so sorry. Never mind. Okay. A b is going to take more than one line, just FYI, okay? All right. So who is your outermost function? The sine. So that's derivative of that sine will be cosine. Does the stuff inside change? No. Root cosine of cotangent of 3x. We still have to differentiate the root of cosine of cotangent of 3x. Dana, you gonna make it? You're just giving it like, this noise is making me crazy look.
Unless you mention it, I don't notice that.
Okay, good. All right, now with this thing, what part of that gets differentiated next? Hands giving, oh my God, this is crazy face. So what's the outside function there? X to the 1/2. Does that make sense? That gets differentiated next. So the first part just copies down. Like, I know it's crazy and it's gonna take some paper, but like you can do it. So the stuff to the 1/2 is 1/2 all that stuff. And what's the new power in the stuff? What's
Negative 1/2.
-1/2. And what still needs to be differentiated? Cosine of cotangent of 3x. Oh my God. Okay, is that okay? But you understand that? Okay, do you understand how you break it down step by step?
Yeah.
Okay. With these first two pieces, I'm going to make them a fraction. Cotangent 3x. And the denominator is the 2 and the root cosine of cotangent 3x. See what I did there? You wish that stuff would cancel, but can it? The reason is because first this stuff in the top has to be cosigned, right? So this doesn't cancel that. Suck. Which means psi in Swedish. So you can like say, okay, now differentiate this piece. Who gets differentiated next? Who's the outside function now? Cosine. Cosine's derivative is negative sine. and the cotangent of 3x stays inside, times derivative of cotangent 3x. And now you're almost done. Okay, you can do this. Cosine of root, cosine cotangent 3x over 2 root cosine cotangent 3x times negative sine cotangent 3x, and then we're going to do last bit fast. What's the derivative of cotangent? Negative secant squared, 3x stays, just a second, Natalie, and then times one more chain rule. What's times derivative of 3x, which is just 3. Okay, Natalie, what was your question?
On the second one, what happened to the code on the very last one, the very last box?
This one?
Yeah, what happened to the cosine with this?
Cosine is the outside function.
Yeah.
Its derivative is negative sine. You see that? So here you had a root, right? What's the derivative of the root? The root's derivative is 1/2 stuff to the negative 1/2, right? This is the thing that's still being differentiated. Now the question is, what's the outside function on this guy? The outside function is cosine. Cosine's derivative is negative sine. The cotangent's left alone. Okay, what's the final thing you could do, but we're not gonna because we ran out of space? You could just put all of this stuff in the numerator, right? And that stuff in the denominator, and then what happens to the negatives? It's not a trick question. What's the negative and the negative? Positive, just gonna cancel out, right? Okay. So, okay, you make me think you need to write the final answer.
So why would you do this?
Why wouldn't I take the derivative of the negative sign?
Because it's inside. Couldn't you keep going?
No. Okay, so if I just gave you the derivative of cosine of cotangent, like just that, nothing else, okay? How would you do that? Who gets differentiated first? And its derivative is, what happens to the cotangent? Stays in there, and what do you multiply by? Derivative of cotangent, which is okay. Now, that's the same thing we did here. The thing is that differentiating that composition means differentiate the cosine first, that's that part. And this is the whole f prime of g part in the, okay, does that make sense? Yeah. So that part is no longer being differentiated, it's done. And this is the whole times g prime part, and that's why there's a derivative symbol there. Okay, yes, Anne?
Outside of a math class, where would something like this actually?
Oh God, this one's just a math class question. Yeah, there are definitely applications that involve compositions that don't involve cosines and sines. This one's a puzzle. It's a can you dissect it puzzle, yes.
Is there gonna be questions like this?
Yes. Yes, there'll be questions like this on the homework or quiz. You just have to deal with it. Okay, keep track of it. Is big long thing at the bottom. Yes. Once you get good at this, you can really do it in one line and keep track of what you've done and what you still have left to do. So, like by the time you're with this like section, hopefully you'll be able to do that a little bit faster. Like write fewer steps. Okay. I believe in making you think. All right. I'll give you more space next time, yes. It actually helps if you've got like a long space.
The final answer is a big, long.
All right, find the points where the tangent is horizontal. So what do you have to find to figure out where the tangent is horizontal? Start with the slope is 0, yep. And to take this derivative, you have to use the chain rule. because that's cosine of x to the second power. So what's the derivative of the 2 cosine x? Negative 2 sine x. And the next part. Who's the outer function in the cosine of x squared? The x squared, so first the 2 pulls down, the cosine's now raised to the first power, times the derivative of cosine, which is negative sine. Okay. Set that equal to 0. Don't divide by stuff that's got variables in it. Take out greatest common factors. So, yeah, what is the greatest common factor?
Negative 2 sine x.
Great. Times, I think 1 plus cosine x, right? So you've got 0 equals negative 2 sine x, and 0 equals 1 plus cosine x. Oh, that's a terrible circle. Can't even. Okay, on your unit circle, when is, so sine is the y on the unit circle, when are the y's 0? Or is the first 0 and pi and 2 pi and 3 pi and 4 pi, etc., right? So x equals pi n. Does that make sense? Sine is 0 if x equals 0, pi, 2 pi, and also all the negatives. Sine is the y. When are you up nothing? How about 1 plus cosine x equals 0? I don't think that's pi. Oh, it is pi. Never mind. Sorry. Cosine x equals negative 1. That's at x equals pi. And then also 3 pi, right? 5. That'd be x equals pi plus 2 pi n, but do you really need that? So the question is, are all of these numbers already accounted for in the previous list? Yes, so then all you need is that list. So this gets both. Lovely silence. Yeah. I think I will dock you a point if you don't recognize that you only need one of those. Yes, you have to be thinking about it. Ask yourself did those numbers get listed already? Yes. Okay, 100th derivative of something. This is also going to follow a pattern, but it's easy, but not quite as easy as the last one that we did. So first of all, what is y prime? Cosine of 5x, and then multiplied by what? Because of the chain rule. 5. So that's the same thing as 5 cosine of 5x. Okay, what's the second derivative? So still got the 5, right? What's the derivative of cosine of 5x? How would you guys tell me? What's the derivative of cosine of 5x? Negative sine of 5x multiplied by another 5. So can I write that as negative 5 squared sine 5x? You could say 25, but I'm just going to leave it as squared because it's just going to get big quickly. So third derivative, negative 5 squared. What's the derivative of sine of 5x? Cosine 5x, and then times what from the chain rule?
5.
Another 5. So negative 5 cubed cosine 5x. Okay, fourth derivative. Cosine's derivative is negative sine, and multiplied by what because of chain rule? 5. So that becomes positive 5 to the 4th sine of 5x. And the 5 to the 4th isn't back where you began, but the sine of 5x is, right? Back to the original category. Okay, so fourth derivative is that, that. Third derivative is this. Second derivative is that. First derivative, here we go. Okay. So if you want the 100th derivative, so that's why 100 in parentheses, that means derivative, that's how you signify that. What's the power on the 5 going to be? 100, that part's pretty obvious, right? Because every time you take a derivative, you might get a 5 from the chain rule. Now the question is are you sine or are you cosine, or are you positive or are you negative? Does that make sense? The two things you got to answer. And the way you figure that out is you take 100 divided by 4, which I think just is 25 with remainder equal to 0, right? And that means you're back in the original category. Because this is 1, 2, 3, 4, 5, 6, 7, 8. Yes?
Would it also be like, it's an even number, and like y2 and y4 are both
Oh,
sine? Like,
yes.
whereas, like, y1
But
and
like
y3
if I'd asked you for the 102nd derivative, then you're right. Then it would be, they both involve sine, but the 102nd derivative would have to also be negative. Just like the second derivative is negative. Does that make sense? There's two cycles that are going on here. There's the cycling of the sine and cosine that flip-flops. There's also the cycling of the sine, as in the positive, negative of the number, right? So you see how they go positive, negative, negative, positive, right? They flip-flop cosine, sine, cosine, sine,
Got it.
but there's also the negativity that's moving.
Okay.
So this will be positive sine of 5x.
What would cosine?
No, it would definitely be sine. This time I know I'm right. So if you get a remainder of 1, you're in the same category as the first derivative. If you get a remainder of 2, you're in this first derivative. If you get a remainder of 2, you're in the same category as the second derivative. Remainder of 3, you're in the same category as the third derivative, and you don't get remainder of 4, that's remainder being nothing, you're back in the original or the fourth derivative. Okay, what, Natalie?
I think I was just gonna ask you, like, how, again, like, how did you know it was gonna be positive, but I think.
It's because the remainder is nothing, that's why.
So remainder 4 is the remainder.
Remainder 4 is the same as remainder 0, right? There will never be remainder 4 if you're dividing by 4, right? You can think remainder 0 means you're in the original category, or the start. You're back to go. If you start counting from 0, it's 0, 1, 2, 3, right? And this is division by 4 because the cycle's in a cycle of 4.
So we're never the first derivative.
Well, what if I asked you for the 101st derivative? Dividing 101 by 4 would have a remainder of 1, right? Which means you'd be like the first derivative. So it would have been 5 to the 101 cosine of 5x. If the remainder would have been 2, it would be this and then the sine, and then 5 to whatever number of derivative it was. Okay, I know I'm going over, but my plan is to finish this lesson, and then the next lesson you're going to work on is practice. I'm just going to finish these last 2 examples and go from there. And probably just example 12, well, maybe we'll do 13, it's not very hard. Okay. So let's see if I didn't fix this. So this is a question that deals with how your blood alcohol changes when you drink. So this is for 8 male subjects. I made a bit of a typo. This exponent right there should have instead said negative 0.0467 t. So the result of the data were modeled by this function. So this C of t will tell you the concentration of alcohol in their system at a given time. So how would you figure out how quickly the alcohol in their system was changing? What would you use? The derivative. And to take the derivative of this C of t function, notice that you have a number times t and then e to the something. You see what I mean by that? Okay, so then you're going to need to use the product rule. I should say C prime of t. So C prime of t is 0.0225. What is t's derivative? One times e to the negative 0.0467 t plus 0.0225 t times what's the derivative of this e to the power? Same thing, yep, e to the power. And does it change because the power is like different? What do you have to multiply by to account for the chain rule? Negative 0.0467. Whenever you have something inside of a function that's not just t or x or y, you have to use the chain rule. That's how you can tell. If the something inside your function is something different than just a singular variable, then you have to use the chain rule. You see what I mean? Okay. How would you find the rate of increase of the blood alcohol consumption after 10 minutes? What would you do? You'd plug in 10 for t. And if you do that, you're going to get 0.00752. And that's milligrams per milliliter per hour. Because C is measured in milligrams per milliliter and T is measured, per minute, sorry. How would you find part? And so what's happening to their blood alcohol concentration at 10 minutes? Is it increasing or decreasing? So should they go drive? Depends, but probably not, right? Because it's going up. Your body's actually processing that alcohol. How about how fast is it decreasing a half an hour later? They gave you a bit of a hint as to what the sign of the answer should be. Should it be positive or negative? It should be negative. And what number would you plug in? 30. And that ends up being negative 0.0022 milligrams per milliliter per minute. Okay. But the point is you have to use the chain rule when it's e to the anything but just t. And then last one before we take a break and do the worksheet together. So length of day. So the length of day is given by this function. That's in Philadelphia, so their swing won't be as big as ours. So use this to compare the number of how daylight is increasing on January 15th and March 21st. So if you're going to talk about the rate of change of the daylight, you have to find the slope, which is the derivative, right? So L prime of t. So what's the derivative of 12? 0. Okay. With the sign of the stuff, who's the outer function? Sine. So sine's derivative is cosine. The stuff inside, weird as it is, remains unchanged. And then because there was something other than x or t inside of that function, you've got to multiply by that stuff's derivative. So what is the derivative of that stuff? 2 pi over 365. No t. Because if you have the derivative, say you had like 2t minus 80, what would the derivative of that be? Just 2, right? If this was your y prime is just 2. If you have a number times something to the first power, you also could think that this thing distributes, right? And that's the same thing as 2 pi t over 365 minus 160 pi over 365. What's the derivative of the 160 over 365? 0. And this is just a number times t, right? You could think that's t to the first, but 1 pulls down, the power becomes 0, anything with 0 power is 1. You want to apply that rule. It's a line with a ridiculously weird slope and a ridiculously weird y-intercept. That's all it is. Okay, and then how would you compare these? You'd plug in what number for t first? 15. And that gives you 0.021046. And then 80 gives you 0.0482. What are their units? What's L measured in? Hours. What's T measured in? Days. Or it's hours per day. You could convert them into minutes by multiplying by 60 if you wanted to. It's approximately 1.23 minutes per day versus 2.89 minutes per day.